Hello, and welcome to today's webinar hosted by NXP entitled Machine Learning at the Edge, Visual Intelligence with a Low-Cost MCU. Today, we will be joined by our partners at Ozone as we demonstrate the practical steps to go from concept to deployment of MCU-based intelligent vision sensors for your machine learning application. Today's presenters are Anthony Hurica, Senior Systems Engineer at NXP, and Sebastian Taylor, Vice President of Research and Development at Ozone. Before I hand it off to Anthony, I invite you to submit questions during the presentation by using the questions window in your GoToWebinar panel. We will address as many of your questions as possible at the end of the presentation. With that, let's get started. Please go ahead, Anthony.
Thanks, Megan. So my name is Anthony Hurica. I'm a systems engineer here at NXP. And for the very first part of this webinar, I want to talk a little bit about what you can do with embedded ML, what NXP has in terms of software and hardware to enable embedded ML, and touch a little bit about Eiq Toolkit, and then I'll hand it off to Sebastian, who will go into details about our new Eiq Toolkit and all the amazing things that you can do to create your own ML applications using that tool. But first, I want to talk about what you can do with the embedded ML space in general. So there's three main categories that we see a lot of customers interested in. And the first one of that being vision. And this is where you take a camera and you can automatically analyze that camera input and make smart decisions based on what that camera is seeing. And so that can be everything from object recognition and picking out, where the car is or the bicycle or the human, to gesture control, to security video analysis, and a wide variety of other applications where normally you would have to have a human looking at that data, but now you can have your ML model looking at that data and doing it all automatically. The same extends to things like voice and sound. You're all familiar with, Hey Google and Alexa, where it's understanding that you want to give it a command. And so instead of having a human hear that data and then making a decision based on what it's hearing, you can have an embedded ML device doing those kinds of smart things. This also goes for like alarm analytics, like breaking glass or a crying baby, or any other kind of sound profile that you want to be able to recognize. And then the last category that we see is the time series data. So this is where you're taking sensors like an accelerometer, magnetometer, water sensor, or any other kind of sensor that you can imagine, and feeding that into a model so it can make smart decisions based on very complex systems. And so that way you can tell if there's some sort of anomaly that could be happening, and you need to do predictive maintenance on that before it actually fails. So for today, we're going to be focusing on the vision part, because that's where Eiq Toolkit can really help create these kind of exciting new models. So I also want to touch on probably the most common question that we initially receive is, what kind of processor do I need to do embedded ML? At the end of the day, ML inferencing is just basically doing millions of multiply and accumulate math calculations, which most any MCU or MPU can do. There's no special hardware or module that's required. And so really it comes down to, how long is it going to take to run the inference on this model for it to make a decision? Do I have enough flash and memory to store the model itself and the inference engine, and enough RAM to store the intermediate calculations needed to do all this? And that's all going to be very application dependent. And so you can have an image classifying model, but if you're only looking at trying to classify an image into one of two categories, say it's looking at shirts, and you determine if it's a blue shirt or a red shirt, that can be a much simpler model of much simpler performance requirements on the device side, versus if you have a particular application where you're trying to take that same camera data, but divide it into 1,000 different categories and a variety of lighting and positions and backgrounds. And so it's going to take a much more complex model that's going to require a much more complex processor to do that inferencing in a reasonable amount of time. And of course, the reasonable amount of time is going to be very application specific. And so it's very hard to say up front, exactly what that's going to be, because it is so application dependent. But in general, we see typically applications doing simple image classification can be done with an i.MX RT microcontroller family. And that's what we're going to be focusing on the presentation today. Whereas object detection, where it can pick out different objects within a single image and create bounding boxes against it, require a bit more complex model, and so typically we see those targeted for the i.MX applications processor family, which is our Cortex-A, much more higher power devices. And so that all falls in our NXP edge processing continuum. So here at NXP, we have devices that cover everything from the low end to the high end. And where we see a lot of the ML interest is what we call the embedded ML sweet spot. And so that contains our i.MX RT microcontroller family, which are Cortex-M processors, but running at gigahertz speeds or 600 megahertz speeds, on up to our i.MX application processors, which are running Linux and running above 1 gigahertz. That's not to say that you can't go necessarily down to the lower end. It's just that these flash and RAM and processing speed requirements often don't make it feasible for a lot of applications, but again, it's going to be very application specific. So for this presentation, we're going to talk mostly about the crossover section of this continuum, which kind of marries the features of the low-end Cortex-M processors with the real-time analysis and ease of use with a lot of the features and flexibility of the application processors in our i.MX. So you kind of get the best of both worlds. And so you can see a snapshot of our i.MX RT family. We just launched the RT1160, which is a 600 megahertz Cortex-M7. We also have the 1170, which is a 1 gigahertz Cortex-M7, both with a significant amount of internal SRAM. And if you need even more, then we have like the RT600 and RT500 families. And so we kind of have a device for all the different levels that you might need for your particular application. So we want at NXP to make it very easy for you to be able to run your neural networks and models on our silicon. And so to do that, we've created our EIQ ML software libraries and development environment. And so it's a collection of development tools, utilities, and libraries for building ML applications. And this goes all the way from data preparation and training to validation to deployment and inference on our MCUs and MPUs. And so you can take our EIQ software and use it as part of your existing workflow if you already have your ML development flow created and you just need to be able to deploy that model on an embedded system. Then we have several options for that. Or if you're starting from scratch and you don't have anything at all but a great idea that you want to put into reality, then we also have that whole flow covered. And so that's what we're going to be talking about today. So it covers the model creation, and that can be done with the Eiq Toolkit, which is what we're going to be focusing on for the rest of this presentation, as well as the integration and optimization of inference engines. And so we offer these different options because some of them are going to perform better for certain models. Some customers have particular needs where I want to stick to open source, or I want the absolute fastest. So we give you options so you can find the best fit for you. All of these are integrated then in our standard enablement with the Octo for the i.MX or MCU Expresso SDK for the MCU side of things with i.MX RT. And then we provide a lot of documentation and training collateral, hands-on videos to teach you how to use all these tools and provide labs so they're very easy to get up and running, and you can take your model and get it running on an embedded system very, very quickly. So you can see a chart kind of what inference engines are supported based on the particular device. So for most of our i.MX RT devices, you can pick between DVRT, TensorFlow Lite for microcontrollers, and Glow. And we won't have time to go into details of all of this, but there are more details online. As part of that training, we have the MLAI training series. Over 20 training modules that go into details of all these different features and how to use it with hands-on labs for both MCU and MPU. So I highly recommend checking that out. But let's go dive into the Eiq Toolkit. This is a new piece of EIQ enablement that we're really excited about. We've seen a lot of customer interest from this. And the idea is that you can take one of two different paths, either bringing your own data, where you take images that you have that you want to train, and it walks you through step by step how to do that training. Or if you already have your model created, then there's a tool to do model conversion and optimization and quantization, and you can then target that for the different inference engines as part of EIQ. And so they all kind of work in conjunction of both the Eiq Toolkit, of creating that model or bringing in a model, and then being able to run that on our different edge-first processors, be it the Cortex-M or Cortex-A application processors, regardless of which inference engine, it all kind of is intertwined. So the EIQ Toolkit eases that development experience. So Eiq Portal is a GUI that provides a very easy way of creating your own custom vision-based model. We also have the EIQ Marketplace, where if you need additional application packs, development packs, example models, those are available through our partners at Ozone to speed up your development even more and provide some in-based examples of what you can do with these tools. And so this EIQ Toolkit, it can be downloaded from NXP.com. It includes the EIQ Portal GUI as well as the command line tools for model creation, conversion and creation. You can use either. And it's targeted for image classification and object detection models, so for vision-based models. And so this will help you create those models, and then you can take the end result of that and run it on our NXP devices. And so when you open up the Eiq Portal, you'll see a screen like this, where you can create a project, open a project. Its output is compatible with the different inference engines available for i.MX RT and the i.MX applications processors. And you can even do model profiling on the actual system, and it'll tell you which layers took which amount of time, so you can use that to try to optimize your model and make it run faster. So with that, I'm going to hand it over to Sebastian, and he's going to walk through the bring your own data workflow and how you can use that to create your own model.
Thanks, Anthony. Sebastian couldn't make it to this part of the webinar, so I'm stepping in for him today. He will be able to join us later, though, for the Q&A, so please stick around for that. As you said, we'll be focusing on the bring your own data workflow today. What that means is we'll be performing the data curation, building the dataset, including a demonstration on how you can import images from your camera, and then annotate that image with the objects of interest captured. From there, we'll be moving on to model selection. We'll talk about some of the various model options, and then we'll be training a detection model and showing the model training, optimization, quantization, and then doing model validation. Showing that the quantization maintains very high levels of accuracy through edge cases where maybe you get a lower precision, and how we're going to correct that. From there, we'll be deploying the model to our target. We'll quickly show the layer by layer profiling, and then we'll go through and show the detection model running live on a microcontroller device. So that's exciting, live detection on a microcontroller. The platform will be running on the Dpuvision Micro Kit. This is Ozone's camera device for rapid prototyping. It's based on the i.MX RT1062 microcontroller. It's got an integrated OmniVision 10626 camera sensor with high dynamic range, and it comes in a very small package, about the size of a couple quarters, so it's really great for prototyping. We also offer the Maven Edition, which is the Micro's big brother. It's based on the i.MX 8M Plus platform with a powerful MPU for the ultimate inference performance, with state-of-the-art models running at over 30 frames per second in under 4 watts. Both platforms are great. They address both ends of the spectrum in terms of machine learning performance, but today we're going to show you what can be done on the microcontroller. First, we've got our laptop, which will be running the Eiq Portal training models, which will then be deploying to the Vision Kit Micro to do the inference at the edge, including object detection of the playing cards. So that's over here. We'll be detecting them on the camera and sending the results back to the laptop. We are now in the Eiq Portal, and we've got the dataset which has been prepared ahead of time. If you look at some of these samples, you can see the images here have a few annotations. We have a multitude of different card suits and numbers. Now, if you want to bring in more images from the camera setup, we can do that using the remote devices and capture feature. Here, we can see that we've got the RT camera, that's the Vision Kit Micro, and it's at this IP address here, and we'll show it up in the remote device capture over here. Now if we just click on this once, it'll capture an image, the current image from the camera. So now I can go in here and create new annotations for each of the playing cards we've added in the face value labels. If I want to edit the box a little bit, I can just click there and make some adjustments to it, and then we can pick which groups that the images should be in. In this case, we'll go and put them into the test group set. It can go in either train or test. When you're training, it reads the images from that collection, and test is used during validation. We can see that now it shows up here, and we've expanded our data set. This exercise is fairly quick, but you do need a decent number of images, especially for detection data sets. So you're going to want a good data set with bounding boxes of the objects you're looking for. Now this is just a few images. When you think of big data sets, you know Coco has over 100,000 images. It's 20 gigabytes. To train smaller data sets, when we have limited images like this, the Augmentation Tool is quite helpful. So click Augmentation over here. Under this tool, what happens is it will randomly make modifications to all the images during training time, as sort of a way to eliminate having more samples in the data set. Now this is managed through the pipeline. So there are some default pipelines, but if we were to go ahead and create a new pipeline, we can say, for example, add in a random blur. So if we open this up, there's visualization. This one over here controls the visualization. So if we turn this up all the way, we can see what a heavily blurred image looks like. And if we turn it down, we can see different levels of blur. We can use this to gauge what the maximum threshold for the Augmentation Tool should look like. Even as low as 14 for cameras this blurry should be focusing the lens, so we'll adjust this down. And then this will give us a level of blur and the way it works. So probably 0.5, so there's a 50% chance that this will apply a random blur. And then it'll randomly pick a value inside the minimum maximum. If we inspect here, we can see there are various other types of augmentations. The tutorial will tell you an idea of what you can do. Rotation is a pretty useful one, especially for detection data sets where the card could be in any kind of orientation. Now, things to keep in mind, it's rotating the whole card image, but you can see it does correct for the bounding boxes in it. So it doesn't remove the need for having a good data set, but it certainly helps improve the number of images that are presented to your model. Next, we can look at the model selection. So Eiq Portal ships with a number of base models. The base models are over here, and I can show you that list. We've got the MobileNet models, versions 1 through 3, as well as 2 different SSD models, and all 5 can be used for training. So if we were to select detection model with a higher performance for the MCU, what it does is it said based on the selection you've made of wanting to train a detection model that you're going to run on an MCU and you want it to be more performance optimized, it picks a model and configures the initial parameters. So the initial parameters are optimized for a smaller scale model in this case. And you can still go and customize it for whatever your needs are. There's also the ability to have user models. That's a whole other topic other than today, but effectively you can implement your own model using the Crass API, and then there's a plugin API for exposing these parameters. All that can be user defined, which is quite useful. And then finally, the model pack add-on. This is an offering from Ozone where we specifically optimize models for different NXP silicon. So if you're looking for a model that's well optimized for detection on the RT1064, for example, we've worked on models where we've focused optimization specifically for that use case, the best possible performance out of the DeepView RT on that specific target. For the video today, we'll just look at one of these default base models that's available to everybody. So the base model we picked is the SSD MobileNet V3, and then from here we can pick a number of different parameters. The first one is the weight initialization. So this is a collection of pre-trained weights, basically for transfer learning. You'll see that there's a MobileNet V3 small and large in this base version. So this is what ships with like Crass models, but basically what was offered on the MobileNet V3, original open source distribution, and then a VOC retrain model you can also train for random weights. And then finally, you can create your own basic type of transfer learning. So I could train a project here, and then go pick another model, and say from File, and select previous checkpoints loaded into here, and there's all sorts of examples where this could be extremely useful. Maybe you've got your own local VOC or COCO open image dataset that you want to train custom models on for random weights, and then later you want to specialize it for smaller datasets. So you're able to save from file and basically transfer learn from those weights. So transfer learning doesn't have to be from publicly published weights. It can be from your own generated weights. So in this case, we'll use the default small weights. There's controls for input size, learning rate, and batch size, and we'll leave these all in default epochs to train. Typically, especially for detection models, you can adjust this up, and what you really want to do is go all the way to infinity and then set a stop condition. Generally, what I like to do is just say stop at target. So basically, once it reaches 100% accuracy, which it will probably never reach, but what this lets me do is train it until I decide I'm happy with it, and then I can just stop the training. The augmentation settings here allow you to adjust the augmentation loadout. So when we created the pipeline previously, we can load that in here. And then the model parameters, this is where the model can expose various parameters that are selected from the GUI. When you're implementing a custom model, there's an API for publishing what's available, and it can be exposed here. So Optimizer for this model works pretty well. So hard switch to find the initial training, which happens in fewer steps, but as we can see in this example, it actually provides a bit of a flaw when it comes to quantization, where RealU6 works much better. So I'll pick RealU6, but we can show if you pick hard switch and train the model to find quantization doesn't work too well. This is another use case where you can come up here and pick that hard switch model as a weight initialization, and then update over here so you can use RealU6 and then transfer from hard switch to RealU6 to kind of speed up generating a model from that first one you trained, which will then quantize significantly better. From here, we can now click Start Training. So this will take a few seconds to initialize the graph and then start training. And then while it's training, we can see things like the model performance, how many images per second we're able to process, and stuff like that. The numbers will vary depending on if you have a CUDA-enabled GPU or not, how big the data set is, how big the images are, and how much processing is required. Now this can take quite a while, especially for detection models, and the time to get a good quality detection model is still measured in hundreds of epochs. We're going to stop this and switch to a pre-trained checkpoint that we've already generated. So if you go back to select model, one of the other options in here was to restore model. So we will restore the model, basically loading a saved project from previous. So over here we can look at this example. We're talking about the issues we had with hard switch. The original model, this checkpoint, if we were to look at the model parameters, we can see it's a hard switch activation based, and we can see that the training graph starts very low but scales up over 99 epochs and has trained to the yellow dots, which are test accuracy, so it's about 82%, and that looks pretty good. But what we find is if we were to then quantize this model, the performance is actually quite poor. So the accuracy, instead of being, say, in the 80% range, is now in the 20 to 30%. So it's actually quite bad. And if you want to learn more about this, there's actually a whole topic on hard switch activation. Basically what it comes down to is there's no clamping, and your low to high values can be in the hundreds, whereas with RealU6, you are limiting the output to between 0 and 6. So when it comes to quantization, you're trying to fit this into an 8-bit integer. The RealU6 just provides a much better conversion from the floating point numbers to the quantized numbers. So if we were to go back and restore the model, we can see this model where we've basically retrained it from the previous model, from this one here, and this checkpoint, so 104 epochs, we can see the blue training graph and the accuracy actually start quite high. And this model has already been trained quite well, but if we change the activation function, and what happens is at validation, the accuracy is actually really, really poor, but over time it comes back and catches up. And the end result is a model that actually performs quite well. But if we were to look in the model parameters, we can see this is now using RealU6, and when we train this model, we validate this model, we all expect that our later quantized validation score is well within a percentage point. So now we're validating on the PC the floating point model, and we can see that the accuracy is 98.53%, so almost 99%. And now we can do the validation on our target with the quantization enabled, and we'll see that the accuracy is fairly close, and we're sending the input and output data types to float 32. This doesn't change the internals of the model, it's just the first and last layer will automatically have quantized and dequantized off, so that from the firmware we're basically treating this as a floating point model. Even though internally it's quantized, you don't have to do that. It's really just a preference on how you want to set up your firmware. But now the validation is complete and we can see we are right around 97.8%. So we lost roughly around 1%, but it still works really well. And we'll see here when we point a browser at the web firmware running on the target, it actually works quite well. So this is the camera setup that we saw earlier. And what happens is it's streaming the live camera feed at about 10 frames per second. And we can see the detection happening. The bounding boxes are being drawn on the cards. And if you were to move one of the cards, the bounding boxes disappear. And then if we were to bring the card back into the scene, bounding boxes will come back. So the bounding boxes are actually updated at 1 frame per second, while the video is updating at 10 frames per second. This kind of shows you an example of a real world detection example that can be run on a microcontroller. And this can be expanded to other examples too, such as the one we have here. It's exactly the same type of idea, but in this case we're actually looking at real cars in a parking lot. And this is a pretty cool example that we've put together. What it does is it monitors where the cars are parked in the parking lot, and it knows where the camera is in the real world. So as you can see, we generate a heat map overlaid over the map showing where the cars tend to be parked in the lot. And this is all generated automatically by one of these little microcontroller cameras, staring out into the parking lot, detecting cars, and then deciding where they are spatially within the parking lot. And you don't need to run very fast for this type of application, as the cars tend to stay parked for a little while. But obviously the faster you can do your detection, the more type of applications open up to you. So as of today, that's roughly about a frame per second, and it's constantly being optimized. And this will allow for more and more performance applications with time.